Okay, so let's continue with time. Jiffy's wraparound. So the Jiffy's variable. Remember, Jiffy's is actually a variable that counts the number of timer interrupts that has happened since the system is booted. It's not actually the time in milliseconds or anything like that. It's the number of interrupts that has happened, if you can think of it that way. So if you really wanted to get the time passed or some sort of duration off of a Jiffy, you would actually have to do some math to infer that, usually through the frequency that's configured in your kernel build. So, just like multiply it by, I think, hertz or something like that. Okay, so, no, that's not right. Wait, hertz. Yes, it was like divided by the number of seconds or something like that. Okay, not that important. Let's just move on. um, The Jiffy's variable, like any C integer, experiences overflow when its value is increased beyond its maximum storage limit. For a 32-bit unsigned integer, the maximum value is 2 to the 32 minus 1. Thus, a possible almost 4 billion timer ticks can occur before the tick count overflows. When the tick count is equal to this maximum and is incremented, it wraps around to 0. So yeah, if it's 32-bit positive integer, it's just going to go after 4 billion, 294 million, whatever. It's just going to go back to 0 and it starts to count again. So here's an example of the wraparound. So let's look at an example of wraparound. So Jiffy's plus hertz over 2. Oh, so it's not multiplied. It's plus in this case. So that's the timeout here. So you want to timeout within 0.5 seconds because hertz here is actually the 1 second is represented by 1 second. So divided by 2 is going to be half a second. And you want something to occur jiffies plus pretty much half that jiffy from now. Okay. So do some work. Basically, if your timeout is greater than jiffies, meaning that in this future, this timeout is actually greater than the jiffies that had was assigned before. It means that we didn't yet experience that future time. Okay, if otherwise that timeout is now less than the current jiffies, then that means that we've already timed out, so the timer expired. So that means that thing that was scheduled in the future has already occurred. Okay. So the intention of this code snippet is to set a timeout for some time in the future, for 1/2 second from now. In this example, the code then proceeds to perform some work, presumably poking hardware and waiting for a response. When done, if the whole ordeal took longer than the timeout, the code handles the error as appropriate. And it's not necessarily an error. It's error in this case, but expired timers just means it's time to just act on something. Multiple potential overflow issues are here, but let's study one of them. So this does not handle the situation where your jiffies wrapped around, right? So this always assumes that jiffies is always in a good state. So this code here does not handle that edge case. Okay, so consider what happens if jiffies wrap back to 0 after setting timeout. Then the first conditional would fail because jiffy's value would be smaller than the timeout despite logically being larger. That means if jiffies hadn't wrapped around, technically it should have been a larger value in this case. But now with the wraparound, the jiffy's value becomes smaller than the timeout, and so the code is going to assume that the timeout hadn't occurred yet. So potentially not executing the specific piece of code that was supposed to be scheduled half a second until much later because the timeout caused, or sorry, not timeout, the wraparound caused jiffies to become smaller value. So it makes it like one big lap now. Conceptually, the jiffy's value should be a larger number, larger than the timeout. Because it overflowed its maximum value, however, it is now a small value, perhaps only a handful of ticks over 0. Because of the wraparound, the results of the if statement are switched. Whoops. Thankfully, the kernel provides 4 macros for comparing tick counts that correctly handle wraparound in the tick count. They are in linux/jiffies.h. Listed here are the simplified versions of the macros. So here's how you can actually tell that given some sort of time, like current value of your jiffies and the jiffies before, you can see whether or not this current jiffies is actually occurring before, after, or whether or not, I guess, equal, like, at that moment, or in the future, or at that moment or before. So these are little helpers that you can use. So you'll just do time after plus the jiffies now versus the jiffies you knew of prior. Okay. So the unknown parameter. So you'll actually use this in your checks. You'll call them like these, and that's how you'll figure it out based off of the result. I think it'll just return true or false, given that it just does some math here and it checks to see if it's less than 0 or greater than equals 0 or so on. So anyway, I think the difference here is also that it's switching the terms. So it's known minus unknown versus unknown minus known, and that tells you whether or not something's after or before in this case. So the unknown parameter is typically jiffies, and the known parameters is the value against you want to compare. Okay, so yeah, jiffies is the current jiffies, right? So that's the unknown. That's what you want to check for. The time after unknown known macro returns true if the time unknown is after the time known. Otherwise, it returns false. So the time after macro, given the current jiffies and the known jiffies before, it returns true if the time unknown, so if the current jiffies is after the time that you knew of. Okay, otherwise it returns false. The time before is the opposite, right? So given some sort of jiffies value against some jiffies that you know of, the macro will return true if this unknown time is before the occurrence of the time that you knew of. So otherwise false. And the final 2 macros perform identically to the first 2, except they also return true if the parameters are equal. So they could be equal time. The timer wraparound safe version of the previous example would look like this. Okay, so now let's go back to that half a second in the future scheduling thing again. So we figure out a jiffies value to check for. That is half a second later. So it's just going to be jiffies plus hertz over 2. And then we use time before to see whether or not this current jiffies value is actually still, I guess, in the past, like it hasn't happened yet compared to the timeout. So that means we didn't time out. Otherwise, we could assume that the timeout has already occurred and we're somehow now in the later time. So this is actually the safer way to check it as opposed to this way. Okay? So that's good to know. That means that we're supposed to be leveraging it like this instead of doing the complicated math ourselves. I think this is actually complicated math. So, yeah. If you are curious as to why these macros prevent errors because of a wraparound, try various values for the 2 parameters. Then assume one parameter wrapped to 0 and see what happens next. User space in hertz. In kernels earlier than 2.6, changing the value of hertz resulted in user space anomalies. This happened because values were exported to user space in units of ticks per second. Okay? As these interfaces became permanent, applications grew to rely on a specific value of hertz. Okay, so again, it's not just the kernel that has to keep track of time too. Like user space, processes are also keeping track of these things too for their own purposes. And there's some inconsistency that occurred because of the way we were exposing things, I guess, from the kernel side of things. So consequently, changing hertz would scale various exported values by some constant, without the user space knowing. So changing Hertz value would cause user space values to be affected, and that would break a lot of programs. Uptime would read 20 hours when it was in fact just 2. So to prevent such problems, the kernel needs to scale all exported Jiffy's values. It does this by defining the user Hertz macro constant, which is the Hertz value for that user space expects. On x86, because Hertz was historically 100, user Hertz is 100. The function Jiffys to clock t, defined in kernel / time c, is then used to scale a tick count in terms of Hertz to a tick count in terms of user Hertz. Okay, so Jiffys to clock takes account of the kernel Hertz and the user Hertz and correctly converts it to a value that user space can actually read. Okay. The expression used depends on whether user Hertz and Hertz are integer multiples of themselves and whether user Hertz is less than or equal to Hertz. If both those conditions are true, and for most systems they usually are, the expression is rather simple. So we return basically given some x, we just divide it by some fraction of Hertz over user Hertz. Okay. A more complicated algorithm is used if the values are not integer multiples. Okay. Finally, okay, so I guess he's not going to discuss that because I don't think it happens often enough. So finally, the function Jiffy64 to clock t is provided to convert a 64-bit Jiffy's value from Hertz to user Hertz units. So remember, there were two types of Jiffy values. One was a 32-bit one and one is a 64-bit one. But the 64-bit is still kind of interpreted and read as a 32-bit value. Okay. So these functions are used anywhere a value in ticks per second needs to be exported to user space. So the following is an example. Unsigned long start, unsigned long total time. Start is Jiffys, do some work, then calculate the total time by taking the current Jiffys here minus the start, which is assigned with the Jiffys then, right? This could have been like some expensive work. Okay, so then the Jiffys would for sure have changed then in that case. But then you already saved the old Jiffys value in start. And now here you can actually figure out the user space ticks here by using the Jiffys to clock t. Okay, so how many Jiffys had passed based off of the total time, basically the total Jiffys from the kernel side of things. Right, this is the kernel side of things, and this converts the total ticks from kernel to the user space side of things. So the user space expects the previous value as if Hertz is user Hertz. If they are not equivalent, the macro scales as needed and everyone is happy. Of course, this example is silly. It would make more sense to print the message in seconds, not ticks, for example. So total time divided by Hertz. That will actually give you the number of seconds. Okay. Hardware clocks and timers. Okay, this one's pretty interesting. So hardware clocks and timers. Architectures provide two hardware devices to help with time keeping. The system timer, which we have been discussing, and the real-time clock. The actual behavior and implementation of these devices varies between different machines, but the general purpose and design is about the same for each. Okay, so first we have that real-time clock. All right, what is this? This person. Wow, this person really was probably doing something with timing or something like that. So the real-time clock. The real-time clock, RTC, that's what he finds as important, or she, provides a non-volatile device for storing the system time. Okay, the RTC continues to keep track of time even when the system is off by way of a small battery included on the system board. So this battery is usually that little coin cell battery on your motherboard. So that we call that battery. It's powering the real time clock. Okay, so on the PC architecture, the RTC real time clock and the CMOS are integrated. So I forgot what CMOS stands for, but that's like your settings for your system board, I think. CMOS. Yeah, CMOS. Okay. And a single battery keeps the RTC running and the BIOS settings preserved. On boot, the kernel reads the RTC and uses it to initialize the wall time, which is stored in the X time variable. So wall time is like the real time of the like kernel, like as since it has been booted. The kernel does not typically read the value again, so it's one time only. However, some supported architectures, such as x86, periodically save the current wall time back to the RTC. Nonetheless, the real-time clock's primary importance is only during boot, when the x-time variable is initialized. So I guess from there it knows how to calculate time. So you only need it once, and that's like kind of like a baseline, I guess. System timer. The system timer serves a much more important and frequent role in the kernel's timekeeping. The idea behind the system timer, regardless of architecture, is the same: to provide a mechanism for driving an interrupt at a periodic rate. Okay, so again, I kind of want to try to review with myself and remind myself that timers, their job, the system timers or hardware timers, their job is to fire a timer interrupt to the kernel, so signal to the kernel, and that kernel, the kernel receiving the interrupt is going to run a function called the timer interrupt handler to do the necessary work that it needs to do to keep track of time, to do things that are time dependent like scheduling, or to also do some management and other things, like for example power management for keeping track of some idle activity and turning off the floppy drives, things like that. So it's not like the timer is there to keep track of time, really. It's to, well, it's not to keep track of time for the kernel to request, but more like it's telling the kernel that some time has passed since the last time it fired, if that makes sense. So it's up to the kernel then to keep track of the real time based off of that information. And that's where the jiffies and all that stuff comes into play. So the system timers is just there to fire an interrupt. And it's up to the kernel to just do whatever it wants to do based off of that interrupt. Okay. All it knows is that that timer interrupt is firing regularly at some frequency. So some architectures implement this via an electronic clock that oscillates at a programmable frequency. Other systems provide a decrementer. A counter is set to some initial value and decrements at a fixed rate until the counter reaches zero. When the counter reaches zero, an interrupt is triggered, and in any case, the effect is the same. Okay, so in any case, the effect is the same. It means that it doesn't matter how this timer is doing it. It's just that the end goal is to just drive an interrupt back to the kernel so that the kernel actually knows that some time has passed since the last time it occurred. Okay, it being the interrupt. So on x86, the primary system timer is the programmable interrupt timer, or the PIT. The PIT exists on all PC machines and has been driving interrupts since the day of DOS. The kernel programs the PIT on boot to drive the system timer interrupt, basically interrupt 0. So remember we had, if we looked at cat proc interrupts, we had like the list of interrupts here. And if we looked at interrupt 0 on proc interrupts, we see that it is the timer right here, interrupt 0. Okay, so that's the interrupt line. So anyway, okay, where am I? Okay, I'll just read this again. On x86, the primary system interrupt is the programmable interrupt PIT. The PIT exists on all PC machines and has been driving interrupts since the days of DOS. Okay, blah, blah, blah. We've been through this. The kernel programs a PIT on boot and drives the system timer interrupt 0 at a hertz frequency. So interrupt 0 is the line that is used for the interrupt signals to pass through, okay, at this frequency, this many times per second. So if it's 100 hertz, it's going to happen 100 times per second. If it's 1,000 hertz, it's going to happen 1,000 times per second. So it is a simple device with limited functionality. So it's so simple. It's just its existence is just to do this, but it gets the job done. Other x86 time sources include the local API-C timer and the processor's timestamp counter (TSC). Okay. Darn it! I clicked on that again. Let's see. Timer interrupts. Okay, there we go. Okay, so I'll do this for another 5 minutes. Okay. So the timer interrupt handler. Now that we have an understanding of hertz, jiffies, and what the system timer's role is, let's look at the actual implementation of the timer interrupt handler. So this is actually the code that gets run whenever the timer sends an interrupt signal to the OS. Okay, so this is the code that actually runs. The timer interrupt is broken into two pieces. An architecture dependent, meaning the interrupt handler is handled in two phases. The first phase is a function that runs that is very architecture specific, meaning that it's specific to x86, ARM, PowerPC, I don't know, Spark, whatever. And another one that is architecture independent. So basically another function gets run after that is generalized. It doesn't really take care of caring about what CPU architecture the coder is running in. So I'm guessing the architecture dependent code, there's going to be variations of it, and a lot of it's going to be assuming on some sort of assembly code, I'm assuming, or like logic that determines the bit length of the CPU. Anyway, the architecture dependent, so the first part of the routine is registered as an interrupt handler for the system timer and thus runs when the timer interrupt hits. So this is the part that runs first when the interrupt occurs from the system timer. Its exact job depends on the given architecture, of course, but most handlers perform at least the following work. So here's the basic logic that executes whenever this architecture dependent interrupt handler runs to handle the timer interrupt. So we first obtain the xtime_lock, which protects access to Jiffy 64 and the wall time value xtime. Okay, so remember, we had to do this in a way where we had to synchronize. There could be many like other processes many threads trying to update this Jiffy 64 value, because this Jiffy 64 value is composed of like two parts from what we recall correctly. So then we had to kind of lock that down and update it correctly. And then also this xtime value, which is the wall time. We had to update that value too to actually indicate that time has passed. So then we have to acknowledge or reset the system timer as required, meaning that the system timer fired that interrupt, right? So therefore, the OS's job is to immediately respond back to the system timer saying, hey, got the interrupt, I'm handling now. Okay, you do what you need to do next. Who cares? I'm handling whatever you told me to do. And so that's the acknowledgement. Periodically save the updated wall time to the real-time clock. So remember, this X time here reflects the wall time. So we had to go and send that information to the real-time clock, the RTC. So, okay, so here's what's going on. All right, so we have the system timer. Okay. And that's going to trigger an interrupt to the OS. Okay. Now the OS will then acknowledge back, okay, ack back, telling, hey, got the stuff, okay. And then what's going to happen is that OS is going to update jiffies, okay, and also in turn update wall time, which is going to be X time. Okay. Not only that, it has to then make access, okay, to the RTC, giving it the new wall time value off from X time. Not yet. Okay, so yes, but I still have to do this for about 5 more minutes, and then I will come help you. Okay? All right. Okay. All right. So, sorry, kids. Okay. So this is first the basic flow that we've outlined here already, and then after that is when we actually call the architecture independent timer routine tick periodic. Okay. So this is the part. This is the second part. The more interesting part that's generalized for all architectures. So this the second function. So then what ends up happening is that the OS now calls into the arch independent. Okay, that means it doesn't matter handler, and that's a function. Okay. So here, all of this is the handling of that timer interrupt that occurs from this piece of hardware. So these two things are hardware. Okay. And it's not that like this is actually making access to CPU or whatever other hardware, and the CPU kind of I think taps to the OS or something. I don't know, but good mental model. This is enough to follow. So anyway, so now here's what the architecture independent routine tick periodic does to perform. Actually, I have a little bit more time after all after checking. Okay, let's continue. So where were we at? Oh, tick periodic. Okay, the architecture independent version, or not version, part of the timer interrupt. So the architecture independent routine tick periodic performs much more work. So it's the heavier part of the timer interrupt handling process. So first we increment the Jiffy 64 count by 1. So that is this part here, I guess. Okay, but that's. Oh, okay, we obtain the lock. All right, so lock. And then after that, we update. So then this is actually then triggering this part right there. Okay, cool. Let me make connection. All right. Okay. So then we finally increment it. So we locked it before. Now we increment it. So then we update resource usages such as basically consumed system and user time. That's I guess for scheduling, right? To say that things have actually been like time has passed for the currently running process. Run any dynamic timers that have expired. So timers that have been scheduled to do something in the future. Execute scheduler tick. And then update the wall time. So again, we were just obtaining locks here. In the beginning, but now we're actually doing the real things. Okay, cool. And then we calculate the infamous load average. So this routine is simple because other functions handle most of the work. Oh, I see. I see. All the stuff up here was they're pretty much separate functions that get called in this tick periodic handler. In CPU, is that because of this current processor? So let's see here. So we lock with X time lock, and then we do K time add, which I think does some updating. We'll see. Do timer, and then we unlock X time lock. So one of these is the wall time stuff. One of these is the wall time stuff, and the what is it? The Jiffy 64. So then after that, we consume and indicate that time has occurred for scheduling things, and then profile tick. I guess that's for benchmarking metrics. Yeah. So most of the important work is enabled in do timer and update process times. The former is responsible for actually performing the incremented Jiffy 64. Oh, here. Yeah, do timer is the one that increments Jiffy 64. Okay. And then we update wall time and then we calculate global load. Oh, okay. So the function update wall time, as its name suggests, updates the wall time in accordance with elapsed ticks, whereas calc global load updates the system's load average statistics. So it's done all in here. Okay. So when do timer ultimately returns, update process times is invoked to update various statistics that a tick has elapsed, noting via user tick whether it occurred in user space or kernel space. So here's update process times. Okay, so we get the current process. So remember, current points to the current process in this context running that got interrupted, or maybe system call. Then what do we do? I guess we get the current CPU, and then we do a bunch of things here. Okay. Um, so let's see here. What is it trying to do? So recall from tick periodic that the value of user tick is set by looking at the system's registers. So update process times, user mode, get IRQ regs. The count process tick, this one here, so given this user tick that was obtained by this call here, it does the actual updating of the process's time. So here's what it does to update the process's times. Given user tick P, and P again is this task struct here, indicating the current process. So we basically update the values to that current process with I guess the converted ticks, okay, user ticks. I think that's all we need to know. So you might realize that this approach implies that the kernel credits a process for running the entire previous tick in whatever mode the processor was in when the timer interrupt occurred. But in reality, the process might have entered and exited kernel mode many times during the last tick. In fact, the process might not even have been the only process running in the last tick. This granular process accounting is classic Unix, and without much more complex accounting, this is the best the kernel can provide. It is also another reason for a higher frequency tick rate. Okay. So next, the run local timers function marks a soft IRQ. So remember, soft IRQ is a way to schedule bottom half handlers for interrupts to handle the execution of any expired timers. Okay, timers are covered in the following section: timers. Finally, the scheduler tick function decrements the currently running process's time slice and needs reschedule if needed. On SMP machines, it also balances the per processor run queues as needed. This is discussed in chapter 4. Yeah, scheduling stuff. And then the tick periodic function returns to the original architecture dependent interrupt handler, which performs any needed cleanup, releases the X time lock, and finally returns. All this occurs every 1 over hertz of a second. That is potentially 100 or 1000 times per second on an x86 machine. 1000 because it can be configurable. Okay. The time of day. The current time of day, or the wall time, is defined in kernel /time/timekeeping.c. It's indicated by struct time spec x time. The time spec data structure is defined in Linux /time h as this. So this tells us how many seconds and nanoseconds has occurred. Okay, in real world time, wall time. Okay, so the xtime.tvsec value stores the number of seconds that have elapsed since January 1, 1970. Is that enough? Oh, number of seconds. Yeah, I think that's enough to hold. Sure. This date is called the epoch. Most Unix systems base their notion of the current wall time as relative to this epoch. Okay, now, what about the nanoseconds? The x time v nanosecond value, TV, and this is a typo here, I think, stores the number of nanoseconds that have elapsed since the last second. Okay, sure. So this'll increment and reset every time. Okay. Reading or and this will get incremented when the second occurs. Okay, so this is basically an offset within that second. So this is the, like, if we had like 3 seconds, right? This will be like the nanoseconds within that, between 3 to 4 seconds that's happening. Okay. Reading or writing the x time variable requires an x time lock. Okay. So x time is not a straight up value. It's a struct, and we need to synchronize. Okay, so it's a struct time spec. That's what x time really is. Okay, so it requires an x time lock to manipulate it, and that is not a normal spin lock, but a seek lock. So yeah, to update x time, a write seek lock is required. So we try to get a write seek lock with with x time lock. Then we update and then we unlock. But when we read, basically we need to actually do that do while loop again. So attempt to retry to retrieve it, and then when we do, we can actually do this updating here. So assuming that we do grab it, we just basically do what? xtime.tvsec is going to be the seconds, and then xtime tv nanoseconds divided by 1,000 is going to be the, was it microsecond here? Okay. Ooh. Okay. This loop repeats until the reader is assured that it read the data without an intervening write. If the timer interrupt occurred and updated x time during the loop, the return sequence number is invalid and the loop repeats. The primary user space interface for retrieving the wall time is get time of day. So that's the user space system call to get the wall time. And it's this is the exact system call that's implemented in kernel time.c, sys get time of day. And remember, we created system calls way back when now. So likely is to tell the compiler that this is going to be a frequent path taken. Unlikely is unlikely to occur. Okay, so yeah. If the user provided a non-null TV value, the architecture-dependent do get time of day is called. This function primarily performs the x time read loop previously discussed. Likewise, if tz is non-null, the system time zone stored in systz is returned to the user. If there were errors copying the wall time or time zone back to user space, the function returns the negative e fault error code. Otherwise, it returns 0 for success. Okay. The kernel also implements the time system call, but get time of day largely supersedes it. The C library also provides other wall time related library calls such as ftime and ctime. The set time of day system call sets the wall time to a specified value. It requires the cap system capability. Wow, that's very powerful. So you can alter that through that system call as long as you have this cap system capability for your user. So I'm guessing root would also be able to do that. Okay. Other than updating xtime, the kernel does not make nearly as frequent use of the current wall time as user space does. One notable exception is the file system code, which stores various timestamps, access modified and so on. Okay, in inodes. Okay, timers. So timers, this is the one where you schedule things to happen in the future. Timers, timers, sometimes called dynamic timers or kernel timers, are essential for managing the flow of time in the kernel code. Kernel code often needs to delay execution of some function until a later time. In previous chapters, we looked at using the bottom half mechanisms, which are great for deferring work until later. Unfortunately, the definition of later is intentionally quite vague. The purpose of bottom halves is not so much to delay work, but to simply not to do the work right now. So we have to not confuse this bottom half handler. Bottom half handlers are work to do, to do but not now, versus thinking about bottom halves as delaying work. We shouldn't think about bottom half execution of interrupt handlers as delay, but rather than just I'm not ready to do the work yet, but whenever convenient. What we need is a tool for delaying work at a specified amount of time. So that's what we really need. Certainly no less, with hope not much longer. The solution is kernel timers. Okay. A timer is easy to use. You perform some initial setup, specify an expiration time, specify a function to execute upon said expiration, and activate the timer. The given function runs after the timer expires. Timers are not cyclic. The timer is destroyed after it expires, and this is the one reason for the dynamic nomenclature. Timers are constantly created and destroyed, and there is no limit on the number of timers. Timers are popular throughout the entire kernel. Cool. So a timer is a linked list. Cool. So timers are represented by the struct timer list, which is defined in Linux timer H. So look, it uses this kernel linked list thing again, this list head. So there's a bunch of these. And I think this is actually what gets inserted into a list of these things that indicates some sort of work to be done at a later time, because here is this expires is most likely the duration, and then this void function inside long function pointer is most likely the handler that will execute or should be executed whenever this timer expires. So the timer handler function, and then the expiration value in jiffies. Okay, and this is going to be a linked list, so this will point to the next timer that was scheduled. This is an argument to the handler, so this thing here is going to get passed into this when ready. And do not touch this for whatever reason. So fortunately, the usage of timers requires little understanding of this data structure. Fortunately, the usage of timers requires a little understanding of this data structure. We don't really have to know it deeply. Toying with it is discouraged to keep code forward compatible with changes. So it's supposed to be very reliable, and so changing it and breaking changes is discouraged. Or when I say changing it, I mean updating it. So the kernel provides a family of timer-related functions or interfaces to make timer management easy. everything is declared in linux/timer.h, and most of the actual implementation is in kernel/timer.c. The first step in creating a timer is defining it. So struct timer list my timer. Straightforward. Okay, but then now we have to populate with some of the values. So next, the timer's internal values must be initialized. This is done via a helper function and must be done prior to calling any timer management functions on the timer. So init timer with this value, the reference, the address, the pointer to the timer list right here. Okay. Whew. Okay, so now we fill the remaining values as required. So my timer.expires is going to be the jiffies from now. Timer.data, that's going to be the argument to the handler, and then your handler is assigned to timer.function. Okay, so the my timer.expires value specifies the timeout value in absolute ticks. When the current jiffies count is equal to or greater than my timer.expires, so that's when you're checking, get the current jiffies value and check to see what my timer.expires has. So if it's equal or greater than, that means that the timer has expired because the current jiffies is at a later time now due to its greater value. So the handler function mytimer.function is run with the lone argument of mytimer.data. As you can see from the myTimerList definition, the function must match this prototype. So this is the handler function prototype, the signature of that function. So all your functions that are going to handle like timer things, they must be declared like this. So anyway, the data parameter enables you to register multiple timers with the same handler and differentiate between them via the argument. If you do not need the argument, you can simply pass 0 or any other value. And finally, you activate the timer with add timer. So you initialize with init timer before you actually fill it all out. And then when you're done, you can make it active by doing add timer. Oops, sorry. Okay, I hope that was not too loud. And voila, the timer is off and running. Note the significance of the expired value. The kernel runs a timer handler when the current tick count is equal or greater than the specified expiration. Although the kernel guarantees to run no timer handler prior to the timer's expiration, there may be a delay in running the timer. Typically, timers are run fairly close to their expiration. However, they may be delayed until the first tick after their expiration. Consequently, timers cannot be used to implement any sort of real-time processing. Okay, since they're not that accurate, they could happen like a few milliseconds after they were supposed to happen, due to like that timer interrupt and scheduling and all that stuff. So sometimes you might need to modify the expiration of an already active timer. The kernel implements a function called mod timer, which changes the expiration of a given timer. So mod timer with your current reference to the timer, the pointer to your my timer, and then the new jiffies value. Okay, it will act as a new expiration value to my timer. So the mod timer function can operate on timers that are initialized but not yet active. Oh, okay. So that's a caveat here. This mod timer will not work for timers that have already been called by add timer. When you do this, you can no longer mod timer. Okay, that's good to know. If the timer is inactive, mod timer activates it. Okay, that's also another important thing to know. That's a side effect now. So, oh geez. Okay, so if it's not active, okay, if it's not running, you can modify a timer, but using mod timer. But if you use mod timer, it's not only going to modify the expiration, but also add it and activate it. Okay. So the function returns 0 if the timer were inactive and 1 if the timer were active. In either case, upon return from mod timer, that timer is activated and set to a new expiration. So no matter what, it's going to activate. If you need to deactivate a timer prior to its expiration, use the del timer function with del timer with a pointer to your timer. And this function works on both active and inactive timers. If the timer is already inactive, the function returns 0. Otherwise, the function returns 1. Note that you do not need to call this for timers that have expired because they are automatically deactivated. Okay, that's a good thing to know too. Deactivation is automatically happening if your timer is already expired. So del timer doesn't really matter in that case. So a potential race condition that must be guarded against exists when deleting timers. When del timer returns, it guarantees only that the timer is no longer active. That is, it will not be executed in the future. On a multiprocessing machine, however, the timer handler might already be executing on another processor. To deactivate the timer and wait until a potentially executing handler from the timer exits, use del timer sync. So the synchronized version of it. Del timer sync with, again, the pointer to my timer. Okay. So unlike del timer sync cannot be used from interrupt context. Okay, now I'm really gonna stop now. We'll write some code next time too. Let's see if we can think about anything like that. So thanks.